Right, we'll continue. Today's lesson will be the mass spectrometry and IR spectroscopy. Let's begin with mass spectrometry. Before we start on mass spectrometry, in fact, we have the basics of the mass spectrometer. If you remember, on the unit 1, on the atomic structure, I explained about the basic functions of the mass spectrometer, the 5 chambers, and the purpose of the invention of this particular instrument, the mass spectrometer, that was in 1818, which was invented by F.W. Aston. The basic functions we discussed in Unit 1, and I'm going to go into advanced mass spectrometry under this Unit 2. Before I begin the mass spectrometer, let me distinguish and try to distinguish the difference between spectrometry and spectroscopy. You can clearly see the topic. It says mass spectrometry and IR spectroscopy. So what's this difference? Why we use mass spectrometry and IR spectroscopy? What's the difference between spectrometry and spectroscopy? It's wrong to say mass spectroscopy, and also likewise it's wrong to say IR spectrometry. So therefore, what's the difference? Now, spectrometry does not spectrometry and spectroscopy both are techniques which is used to identify molecules. When it comes to spectrometry, there is no interaction of the electromagnetic radiation whatsoever, right? There's no interaction of the electromagnetic radiation with the matter whatsoever. But in spectroscopy, there is interaction with the electromagnetic radiation and the matter. So the identification of the molecule in spectroscopy techniques is done by analyzing how molecule of the species interacts with the electromagnetic radiation. So in spectrometry, there's no electromagnetic radiation involved, but spectroscopy, there is electromagnetic radiation involved. That's the main difference between the spectroscopy and spectrometry. To understand how the mass spectrometer works, I'm going to just explain to you the basics again, which we discussed on the Unit 1. We'll start from there. As I mentioned before, the F.W. Aston in 1818, he invented this mass spectrometer. The purpose of invention at that point was to identify the relative atomic mass of atoms and relative molecular mass of molecules, and to find the number of isotopes in a given species. But later on, of course, the modern users of the mass spectrometer has various other uses, like as we discussed on the Unit 1, in space research, in pharmaceutical industry, even in sports. They also check the presence of the steroids in the sample of urine. So all those are the modern applications of the mass spectrometer. So the mass spectrometer has 5 chambers. It has got 5 chambers. Let me introduce you one by one. The first chamber, if you remember, that is known as the vaporization chamber. There you have high temperature in the first chamber. The sample is vaporized by high temperature. So sample is injected here. It's injected here. And what happens? The sample turns into a gas. It turns into gas by high temperature. Then the gaseous sample goes into the next chamber, which is known as the ionization chamber. In the ionization chamber, there is an ionizer, which is an electron gun, which shoots electrons at a very high velocity towards a positive plate. Which shoots electrons at a very high velocity towards a positive plate. So you get the positive ions from the ionization chamber. 99.9% plus 1 ions obtained, and 0.1% plus 2 ions can be obtained. Then the sample, now you know how this ionization occurs by high energy electrons. For example, if this is an atom, or it can be atom or molecule, when the electron from the electron gun reaches or comes close to this electron, remember the electron of the atom or the molecule is attracted towards the nucleus, right? So when this electron from the electron gun, which has a very high velocity, which means both the electrons have the same mass, but this particular electron which comes from the electron gun, very high energy compared to the electron which orbits the nucleus in the atom. Because the reason why the incoming electron from the electron gun has a high velocity, it has a kinetic energy, because it has a very high velocity So when this electron from the electron gun comes close to this electron, there will be a repulsion. There will be a repulsion like this. So that repulsion, this is electron from the atom, this is electron from the electron gun, there will be repulsion. That repulsion, if it is greater than this attraction, what happens? This electron is removed away from the atom, resulting the cation. An electron is removed away from the atom, resulting in the cation. This is how the high electron gun, this is how the high energy electron from the electron gun removes an electron from the spaces. And next comes, of course, if it's an atom, then you get the ion. If it is molecule, then you get the molecule ion. Electron is removed from the molecule, right? And then it enters in the next chamber as the accelerating chamber. You have electrically charged plates. So, the positively charged the particle enters into this. There will be repulsion between the positive plate, and it will move towards the negative plate, and it will travel in a straight line. It will not get deflected towards the negative plate because this whole instrument is under vacuum. So therefore, it will just pass through this slit in a straight line. That's the accelerating chamber. Acceleration is done by high difference in the electric. And then you have the fourth chamber, which is the magnetic chamber or the deflector. The deflector has a huge electromagnet, right? So that the job of the deflector is to deflect this incoming particle as to their mass to charge ratio. As to their mass to charge ratio. If the mass is greater, the deflection will be less. That means the heavy molecules get deflected less. The lighter molecules get deflected more than the heavier molecules, right? The lighter molecules get deflected more than the heavier molecules. Why? Because we know the kinetic energy is half mv squared. Kinetic energy, right? When the mass is greater, the kinetic energy will be greater. When the mass is greater, the kinetic energy will be greater. So that particle will get deflected less, because when the particle is traveling at a very high kinetic energy, the magnet will not be able to pull that particle towards it. So as a result, the deflection will be less. So when the mass is greater, the deflection will be less. When the mass is less, the particle is traveling at a less energy. Therefore, as a result, the deflection will break, right? So the deflection is based on the mass to charge ratio. The deflection is based on the mass to charge ratio. Then comes the next change, is the you have sensitive screen. That is the signals which falls into that is amplified to a rudder, and the spectrum is produced as a bar chart, a bar graph, where the height of it, as you know, represents the percentage, I would say, the percentage abundance of that particular isotope, and the x-axis represents the mass to charge ratio of that isotope. So usually we take the +1 ion, that will be the mass to charge ratio of that. Cat 35, and there will be also pCat 37, right? That is for the, of course, when it comes to molecules, it's a bit more complex. I to get the molecule ion, I think I introduced the molecule ion, fragmentation, all those on the unit 2, right? Is that clear up to this point? Any questions? Right. So let's go back to the tute. That's the basic introduction, which you had done for the unit 1 as well. So all this what I explained here, mentioned here. So now let's see what happens when explain the first point. What happens when you introduce a molecule in the vapor? The sample is vaporized, meaning the intermolecular attractions between the molecules are broken. The vaporization chamber is never atomization chamber. You don't get atoms in the vaporization chamber. So when you introduce a sample, whether it's a gas or a liquid or a solid, it just turns into a gas. Job of the vaporization chamber is just to turn into a gas. That's all. So if it's a gaseous state chlorine, it will be just gas. Then if it's a molecule, and the molecule enters into the ionization chamber, what happens is that high energy electrons knock this molecule, and an electron or two electrons will be knocked off from the molecule. So mostly 99.9%, only one electron is knocked off. I mean, two electrons knocked on, and one electron is knocked off, but 0.1%, very rarely two electrons will be knocked off. So usually for calculation purpose, we just take as only one electron is knocked off unless the question specifies about two electrons. Now, when you introduce a molecule, what happens? An electron is knocked off from the molecule. That results in the molecule ion. We symbolize the molecule ion by M+. M+ is a molecule ion. So this is the molecule. M represents the molecule. This is an electron from the electron gun, knocks the molecule, and it removes the electron from the molecule, resulting two electrons as a product, because this is the electron from the electron gun plus the electron of the molecule. Overall, there'll be two electrons removed, right? So if you introduce chlorine, you get Cl2+. The Cl2+ is known as a molecule ion, also referred to as a parent ion. Now, this molecule ion or the parent ion is highly unstable. I'm going a little bit fast because I have already done this. So if you need to me to be slow down, just let me know, because since we have already done it, I'm just going a bit fast, right? So the molecule ion is unstable. It breaks down into atomic ion and the free radical. So this type of breaking down of the molecule ion into the atomic ions and the free radical, it happens because the molecule ion is unstable. So this is known as fragmentation, right? The fragmentation is a breaking down of the molecule ion into atomic ion and the free radical, right? Atomic ion and free radical. So this free radical is it's removed from the vacuum. The vacuum removes the free radical. As for the atomic ion, it is accelerated, deflected, and detected. The thing is, not all molecule ions undergo fragmentation. Some molecule ions, before it even undergoes fragmentation, it is accelerated, deflected, and detected. So that gives the spectrum a bit complex form, right? If I am to draw this, I'll just jump to the question 4. I'll go back to question 3 in a while. Look at this. If I am to draw the mass spectrum of chlorine, peak at 35, peak at 37, 1:3 ratio. Look at a peak at 70, molecule ion, 72.
You are currently the only person in this conference.
Can you hear me now? I'm sorry, I got disconnected. Sound clear? Right, so when it comes to the molecule ion of chlorine, I mean the mass spectrum of chlorine, you will see 5 peaks, out of which 2 peaks, it will be the atomic ion region, like this 2 peak 1:3 ratio, and you get a peak at 70, which is molecule ion, and then 72, another peak, and 74, another peak. Let me explain what these peaks are. Now, this is the mass to charge value, and this is percentage abundance. So you have 35, 37, this is 70, 72, 74. Now, chlorine 35, we know.
The only person in this conference.
Chlorine 35 plus, and chlorine 37 plus. And in chlorine 35 combines that is before fragmentation occurs. I said part of the molecules, it goes as the molecule ion. You get chlorine 72 plus, 70 plus, and then when chlorine 37 combines with chlorine 35, you get chlorine 72 plus, and then chlorine 37, when it combines with chlorine 37, you get chlorine 74 plus. So you have
in this conference.
4 molecular ions here, and these 4 molecular ions are due to the 3 different combinations of the chlorine. So this 70 is known as M plus molecular ion. This is M plus 2 because 2 units next to the molecular ion, and this is known as M plus 4 peak, which is 4 units next to the molecular ion. This is 70 is M plus, 72 is M plus 2, which is 2 units next to the molecular ion. This F74 is M plus 4, which is 4 units next to the molecular ion. Right, 4 units next to the molecular ion. You have chlorine 35 and 37. So you have this. You get the tallest peak here. This tallest peak is named as the base peak. That is the most intense peak and the most stable peak. And the base peak is usually given the relative abundance of 100%, right? 100%. And the rest of the peaks, the percentage abundance of the rest of the peaks are measured with respect to the base peak. Please copy this for question 4. All right, so we go back to the, we know what is fragmentation, what is molecular ion, right? And when it comes to, say, complex molecules, right, complex molecules, the fragmentation will result in various different types of species. Now, usually, when you have 2 options of the fragmentation, or we know the fragmentation will give rise to the atomic or the cation, which is a complex organic molecule. That will be a carbocation, and of course the chlorine is a diatomic molecule. So in that case, you get the simple atomic ion. But when it comes to complex polyatomic organic molecule, you get the positively charged complex ion, which is carbocation, and the neutral species. Now, the thing is, when it comes to the carbocation, if there are 2 possibilities of forming 2 different carbocations of the same molecule, which means you have option of forming a secondary carbocation and a primary carbocation. I hope you remember the stabilities of carbocations. On the unit 1, we discussed the tertiary carbocations are the most stable. Then comes secondary, then comes the primary. So during the fragmentation process, if you have a choice of forming secondary and primary, then you go into the most stable form, which is secondary. And also, if you have an option of forming a tertiary carbocation and a secondary carbocation, then you select the option of forming tertiary carbocation, which is most stable. So what I want to say in short is that during the fragmentation process, it always results in the species which is more stable. So if I'm to write the carbocations, the primary carbocation